Engineering Mechanics Statics, Lecture 15. This is the last section of equilibrium of rigid body, which is equilibrium in 3 dimensions. The objective is to identify support reaction in 3 dimensions and draw a free body diagram, and to apply the equation of equilibrium. So previously we learned about the reaction force in a 2-dimensional joint or spot. For example, we have a joint like this. Okay, fix on that. So this is the structure. And then one more thing is like this. Okay, so this is for 2D. So for now we're talking about a 3-dimensional joint or spot. So if we turn this support into 90-degree turn, so it will become like this. Okay, so instead of here, your structure is here, but it's, if we put here, so this joint will become a 3-dimensional joint. Okay, if let's say I redraw the 2-dimensional cases, so this is your structure. Okay, this way you can do 2-dimensional analysis, which is x and y. Okay, because the movement is only at one plane. Okay, but for this structure, if let's say I redraw it again, okay, so like this. So not only have one plane, which is x and y here, but also you have another axis here, which is z-axis. So this one we call it as 3-dimensional joint or spot. So how the reaction force will produce in this type of joint and spot. Okay, and then for this one also we can this is for 2D. For 3D, because this is on only one plane, which is x and y, for 3D maybe we can have a ball joint like this. Okay, this is ball joint, so your ball joint can rotate at any direction between the axis of x, y, and z. Okay, so this two joint or spot is one of the example of 3-dimensional case. So this is the spot that I explained just now, which is, this one is ball socket and this one is general bearing. So how can we determine the support reaction at this joint for given loading? So previously we already learned about the support reaction in 2-dimensional joint or spots. So this is the example of the 2D reaction force reaction for support and joint. And then this one also. Okay, so how the 3-dimensional will looks like? Previously is 2-dimensional, so for this time is 3-dimensional. Okay, let's say we go for the first one. Okay, for this type of support or joint, the support reaction looks similar with the one in two-dimensional support reaction, right? Okay, and then this is for ball and joint socket. The support reaction will have three component of force, which is in the axis of x, y, and z. And then for a single journal bearing, the support reaction will have both force and moment in a x and z direction, in a two axis only. And then for a single hinge like this, it has three force and two moment. Okay, so for ball joint, we're gonna have three force here, but there is no moment here because the ball joint is free to rotate at any axis or any angle. Okay, and then for this one is like this, right? Okay, so it will gonna have a force in a fx and y direction, but no force here. Okay, because it's free to move here, the translation back and forward. Okay, back and forward, so there's no tendency the force to create it. And then for the moment also, it only created in a fy and fx position. Okay, there's no moment here because the shaft is also free to rotate. Okay, anything that the structure is free to rotate or free to translate, or there is no tendency of the potential of force and moment to be created, so there is no reaction of force for force and the moment. Okay, and then for the hinge here, okay, let's see, we have a hinge here. Okay, so okay, the hinge here, it has a force in those fx, fy and fz direction. Okay, because it's not free to move on those axes, so it has a tendency of force, potential of force. So there's a reaction of force in those axes, and then the moment, it has a moment in a x and z axis. Okay, but there is no moment in a y axis because the hinge is free to rotate on that axis, but it cannot rotate in a z and x axis, so it has a tendency to rotate, so the moment is created. We also have another type of joint and support, so you need to review each of the support here, and you need to understand why the force is such like that. Okay, for each of the support and the joint, and then this one also. Okay, so you can refer this to your textbook and then study all the type of the joint. And okay, next is equilibrium of equation for 3D cases. So as usual, when the system is in equilibrium, so the summation of force is will equal to 0, and the summation of the moment will also equal to 0. Okay, so before this, for two dimension, you will have three element of equation for equilibrium of equation. Okay, still remember we have a summation of fx, summation of fy, and summation of moment. Okay, So this is for two-dimensional cases, okay, and all is equal to 0 when the system is in equilibrium. But for 3D cases, we will have 6 equation, okay, 6 equilibrium of equation, which is summation of f in x-axis, y and z-axis, and then the summation of moment in x, y and z-axis, and all is equal to 0 because the system is in equilibrium. Okay. The moment equation can be determined about any point, usually choosing the point where the maximum number of unknown forces are present simplify the solution. Those forces do not appear in moment equations since they pass through the point, thus they do not appear in the equation. Okay, this means that for the moment, similar with the previous section or previous exercise, when we want to set up the point of the moment, we need to put the moment at the point where the unknown have many unknown. Okay, let's say before this we have beam like this, and then we have an unknown of ax, ay and ax, and then at b here we have an unknown of by. So instead of putting the moment, the point of moment here, we choose here, because if we choose here, the unknown will be, we will have two unknown. Okay, but if we put the moment, the point of moment here, so we only have one unknown here, so it simplifies our analysis. So same goes to the 3D cases. So if in 3D, you must choose a moment where the moment about the point where the unknown is, it has a money point at that point, at that particular point. Okay, next is constraint for rigid body. Okay, for 3D cases, we will have a few constraints that we need to consider in our analysis. Okay, the first one is redundant constraint. Okay, when a body has more support than necessary to hold it in equilibrium, it becomes statically indeterminate. Okay, means that we have more support than required. Let's say we actually the support can be in equilibrium by using only one support, but in your system you have more than one support, so this is the constraint become redundant. So that support will, that more than one support will produce many unknown. So all these unknown cannot be solved by using only static analysis. Okay, we need other type of solution lah. Okay, and then the next one is a problem that is statically indeterminate as more unknown than equation of equilibrium. Okay, like I said, so we have more unknown, but the equation is less than the number of unknowns, so we cannot solve the equation. In 3D cases, there are also conditions that we call it as improper constraint. Okay, improper constraints means that the body is the structure is actually not in equilibrium condition, because if the structure is in equilibrium conditions, so the structure is static, because the summation of f and summation of m is equal to 0. Y is equal to 0. 0 means that the structure is in static condition, there is no movement. But in this case, because both of the support here is a ball joint, so the structure is free to rotate, or the structure is moving in the x-axis, so which means that the summation of m is not equal to 0. So there is a movement. Okay? When there is movement, so the body is not in equilibrium condition. Okay, this is what we call improper constraint. Another case is like this. If we have a structure like this, and then we apply the force in the body, so the body can rotate. Okay, so this one also, the body is not in equilibrium, or it's not static, so there is a movement here, and then so which means that the summation of all the moment here is not equal to 0. If the summation of all the moment is equal to 0, so which means that there is no movement here. Okay, because there is movement, so the summation of moment is not equal to 0. So this is what we call is improper constraint.